Math Ninja here. So we're gonna take a detour into set theory. So we're gonna hold off from loop theory a while because we're dealing with a collection of sets when we're talking about quotient groups. We're dealing with a bunch of sets. But I never taught you how to show two sets are equal. In fact, I never even really defined you what a set is, what operations you can do on a set, or all those nice things that you should know about sets. So we're gonna take a small detour. And the book I'm going to give you right now is Barber and Jack. It's an introduction to set theory, but I'll send you that through email. Anyone who's following my channel, like that's a nice Vladimir fellow, I don't know your name, but you're a nice person, send me nice math questions. Just send it to me and I'll send you the link with the information and the homework that I sent my kids. I'm still have to think of the homework. Let's see how much I can get done right now before my other kids get here. Actually, no. My other kids, I think I'm not teaching them today. Okay, so the first question is, what is a set? You've probably seen sets before, like sets of natural numbers, sets of integers, sets of real numbers. Cool. What is a set? A set is just a collection. It's a bunch of objects that I have decided to abstract from the whole. So let me give you, so a set is really just given a universe of objects. I choose specific elements of that universe that satisfy some property, or even I arbitrarily choose elements. And by choosing them, the collection of those choices are what forms a set. So, for example, consider, let's do words. Consider NYU, okay? Consider all the people in the world. Then I choose only the students at NYU. The set of all students at NYU. So here, this set is S equal to the set of all X in world, where X is in NYU. Or X studies at NYU. So the reason why this is important is sets, you have to be careful about unless, if the context is not known, you have to say what universe you're talking about. Or in fact, X in worlds, the set S where in, actually, or set X in NYU, or X in the world, X is a human, and X is at NYU. You've probably seen this notation before also. S, or let's say S prime equals a set X where 2 divides X. This line means where. So, here's the thing though, I never told you what universe X has to be in. If this was the universe of stars, saying 2 divides a star, it would not make sense. So it's always good, if the context is not known on the spot, to always write the universe, or X and Z. So consider it's all the S, all the objects where X is an integer, where 2 divides X, so all even integers. We call this set 2Z. Okay, so it's cool. I can just say property, and the property defines a set. But should that be allowed? Can there be any problems? So, okay. It's like explaining the birds and the bees. So I gotta explain this to my kids. Kids, there's something called working mathematicians and not so working mathematicians. So, okay. So, there's people called logicians, and what they do is they care about metamathematics. What mathematics, so mathematics makes things rigorous, because it says what rules are things. But why do we decide on these rules are allowed? What rules are we allowed to use? So it's mathematics on mathematics. That's what mathematical logic really is. That is what mathematical logic analysis major, or let's say working math major, consider, for example, analysis major, analysis, would care, not, in my opinion, not more about they wouldn't really care about the ramifications of logic. They really care about the theory, about the axiomization deductions. Well, some do. There's a mixture of analysis and logics, but it's a field of logic, very distinct from analysis. So, a common example is axiom choice. So, axiom choice is an axiom that many analysis majors will use, especially in the case where they're constructing a vector space. The axiom of choice says, well, light reflecting off. I'm going to get rid of. Oh well. So axiom of choice will tell us there exists a basis for every vector space. But there's weird logical ramifications of axiom of choice. It's bad. For example, Banach-Tarski paradox, existence of non-measurable sets. Damn you, light people. Okay. Let me try to fix this really quick. Okay. 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 So axiom of choice. So there's another problem in I'll talk about that. The analysis majors, they also, even though set theory, even though set theory belongs to the logicians, or it's a mathematics, analysis majors do like it a lot for other reasons other than the meta-mathematics parts. And one of the reasons has to do with uncountability of sets. And what set theory, logicians do in that is they describe a way to say two sets have the same size, have the same cardinality. So axiom choice. So next thing I'd like to talk about, well, we're going to talk about an example and analysis of why they love set theory. But that's going to be later. But the first thing I'm going to go to is explanation, answering the question, why? Why? What? Okay. Why do we need to make set theory rigorous? Why can't I just say a bunch of objects and say they fall under some collection? So the problem has to do with the Russell's paradox that says it's an example of why we cannot make just any set. It says why we have to be a little bit careful. So this is related to a very famous problem. You guys probably all seen it. It's called the Barber paradox. And I'm going to have to write down the thing on the internet because the wording is very, very specific. So we have a barber in this town, and every man in this town has to follow a rule. So I'm going to read up what I have written really quick. And what it says, hopefully it's if you guys can see this, it seems really cool. So the barber obeys the rule. The rule is he shaves all and only those men in town who do not shave themselves. And this is the rule of this town about shaving, because everyone likes to keep shaving. So, as a quick example, Jim. Consider Jim. Jim, let's say Jim shaves himself, right? So he does not get shaved by the barber. Another example is John. John gets shaved by the barber. So John does not shave himself. So now we can ask, does the barber shave himself? So suppose yes.